Now we should hurry and quickly. So now we were talking about the energies, right? So kinetic energy we did, and we also learned about this work energy theory, right? In the previous class, we did this work energy theory, right, guys?
Yes, sir.
Yes, sir.
So now we will learn about three more topics today, right? So first would be conservative forces, and then I will talk about the potential energy. And then I will talk about spring force, and hopefully we can do this energy conservation also. Right, so let us set this goal today. So first is what is conservative forces? So what are conservative forces?
Sorry, I'm late. Sorry. I
No, no
forgot.
worries. Yeah, no worries, no worries. So yes. Hello, Rishita. We just started, right? So you were there when we were doing this work energy theorem, right?
At the start of it, sir.
Yeah. So okay, and we didn't go ahead because all of you guys had your exams, so we just revised those portions. Now, what is so the next topic after work energy theorem, right? So we understood that W is change in kinetic energy, right? So this was K final minus K initial, right? And it was delta K, which was integration of, let's say, x1 to x2 and fx dx. This we did in the last class. So now we will do the next ones. So first we learn about the conservative forces. So the type of forces in which work done doesn't depend on path, depend upon or depend on path, right? Which means that it is path independent, right? So let's say we have two places, right? And we are moving the object from here to here. We are moving the object from here to here. We are moving the object from here to here, right? So let's say this is path 1, this is path 2, and this is path 3. So if we are bringing this object from A to B with a conservative force, right? Then the work done would be path independent, right?
Sir, please can
And
you repeat again? What is the
yeah,
work done?
yeah. So work done, let's say you are bringing an object from A to B, and
Yes, sir.
you are working in the presence of a conservative force, right?
Yes, sir.
So then your work done would be independent of the path that you choose. So let's say you are bringing the object from here to here, you are bringing the object following this path, or you are bringing the object following this path, right? So in all these three cases, work done would be same. In the case of the conservative force, right? Is this part
Yes, sir.
clear? Okay, this is
Yes,
the,
sir.
yeah, this is the first thing. And the second thing is that there is no loss of energy due to this force, right? So no power is dissipated in these kind of forces. And third thing, why this force is important, because the idea of potential energy, idea of potential energy comes from conservative force, right? So potential energy is only defined for the conservative forces. So if your force is not conservative, then there would be no definition of potential energy. Understood, everyone?
Yes, sir.
So what are the examples of conservative forces? So the examples are gravitational force, spring force, and electrostatic force, right? So these kind of or electromagnetic force. So these kind of forces are the examples of conservative forces. And similarly, you will have the non-conservative forces, in which that would be, so that will depend upon the path, right? And there would be some loss of energy in form of heat and others. And the examples of, and the potential energy is not defined for that non-conservative forces, right? And the examples of non-conservative forces are, right? So all the definitions would be same, just you write in the opposite way, but I will write so non-conservative forces. So that are tension, friction, right? So these forces are non-conservative. Okay, so this is how you define the conservative and non-conservative force. And then you have an example that why.
Sir,
Yes, yes, sir.
please can you explain non-conservative force again?
Yeah, so for the non-conservative forces, the path would be defined. So the forces or the work done would be dependent upon the path that you take, right? So the idea, so whenever you have non-conservative forces, then the work done would be path dependent. Then this W1 would not be equal to W2 and would not be equal to W. Whenever you have these non-conservative forces, so let's say if you have this friction, right? So
Yes, sir.
you are choosing one path. So in one path the friction would be different, and in the other path friction would be different, right? So your
Yes, sir.
work done would be different, right?
Yes, sir.
That is
Yes.
why these forces are non-conservative. Understood?
Okay, sir. Thank you, sir.
Yeah, and then okay, so this is an example that you can show that how gravitational force is a conservative force, right? So let's say you have this object and you bring it in here by the action of gravitational force, right? So on this object, gravity is acting, and you bring this object from here to here. So what would be the work done from here to here, right? You brought this object, let's say this is mass m, and this height is h, right? So this would be f dot s. So fs cos theta, right? Your weight is, right, the here the force is gravitational force. And how much is the gravitational force?
MA.
Mg, right? Mg,
Yes, sir.
right? And this is the direction in which you are taking. So your distance is in this direction and your force is in this direction. So what is the angle between F and S?
180 degree.
180 degree, right? So good. So theta is 180 degree. So theta is 180 degree, and F is mg and S is h, and this is cos of 180 degree. So this would be minus of mg, right? Let's say this is work one. Is this part clear?
Yes, sir.
So this is, let's say this is path one. Okay. Now what you do is that now you bring the same object, right? Now you bring the same object from here to here. You are bringing at the same position, right? So in here this is H, and in here let's say this is M, and in here this is the object. So I have drawn it like this. This is the object. Okay. So now you are taking the object in this direction. Your so what are the forces that are acting on this object?
Normal force.
Absolutely right. So this is normal, this is theta, and this is gravity.
Gravitational.
So this is your theta, this is mg. So how much would be this?
Mg sin theta.
Mg sine theta, right? And mg sine theta. So this is theta angle. So with theta, what is the
Sir, cos
Mg
theta.
cos theta.
mg cos theta, right? So mg cos theta, and this is
Mg
mg
sin
sin
theta.
theta. So this is the gravitational force which is acting in this direction, right? This is the gravitational force, and you are taking this object in this place, right? So this is the distance. Let's say this distance is L. So now your gravitational force Fg is mg sine theta, right? And your distance is L. And what is the angle between Fg and L? What is the angle?
So please can you tell where is F?
Fg,
FG.
Fg is this, right? Fg is this in this way.
90 degree.
No, no, Fg and L distance. This is the L distance. You have
0.
from, okay, this is L distance, this is Fg. So what is the angle?
180 degree.
180, right? So your angle between Fg and L is 180, right? So let's say that is cos alpha. Okay, so let me write it as alpha so that you guys don't get confused with these angles. So let me write it as, so let's say this is alpha, this is alpha, this is alpha, this is alpha. So theta is 180 degree, right? So work done by the gravitational force to bring this object from here to here. So now we are choosing this path, right? Earlier,
Yes.
earlier we brought this object from here to here by the gravitational force. Now we are choosing this path, and we are saying that this gravitational force is conservative. So work done should be what? Work done should be
0.
what? Work done should be same, right? Whatever
Yes, sir.
path, whatever path we choose, whatever path we choose for the conservative force, the work done is same, right?
Yes, sir.
So now let us calculate the work done. So this would be Fg and dot S. So this is Fg S cos theta. And we know that angle is 180 degrees. So this would be Fg, which is mg sine alpha. S is L and cos theta is minus 1, right? Which is cos 180. So let me write it as cos 180 so that you guys don't get. So this is cos of 180. So this is minus 1. So this would be minus mgl sine alpha. In the previous case, what did we get? What was the work done?
Minus mgh.
Right, but we are getting this work done in this case. In this path, we are getting this work done. So this should be same, right?
Yes, sir.
Okay, so can you guys tell me what can we do with these two? So let me draw this diagram here. You have this alpha, you have this H, you have this L. So how alpha, L, and H are related? Yes. How these three are related, guys? Okay, so let me ask you the trigonometric
Sir, cos.
cos. This is perpendicular, right?
Yes,
This
sir.
this is hypotenuse. So what should be there?
Sir, hypotenuse is h or l.
This is the hypotenuse. Opposite to 90 degree, that is the hypotenuse, right?
Yes, sir.
So don't think about the naming, right? This is height, not the hypotenuse. This is height of h, not the hypotenuse h, but height of h. Okay. So sine alpha would be how much in this case?
H by l.
H by L. Good. So H by L. So put this value in here, right? So what we will get? We'll get mgh and H by L. So this will cancel and we'll get minus of mgh. So work done by gravitational force, this doesn't depend upon the path because W1 is W2, right? That is why this implies that gravitational force is conservative. So this was the idea of conservative and non-conservative forces. Is this part clear, everyone?
Yes, sir.
So please note it down, and if you have any doubt, please ask. So whenever you guys have noted it down and want me to scroll down, please.
Finish, sir.
finished. Okay, then uh,
Finished, sir.
yes, whenever you guys want me to scroll down, please add it.
Finished, sir. Finished, sir.
Done, everyone?
Yes, sir.
Good. So now let us understand about these very crucial terminology. So one is external system, right? And one is internal, right? So one is internal agent and the other one is the external agent. So let's say that you have, let's say we have this Earth, right? And then there's this object which is placed on this Earth, right? So these things are coupled together, right? So this Earth is exerting some force and this object is exerting some force in this. So this is an internal system, right? This is the part of the system, right, everyone? And let's
Yes, sir.
say,
Yes, sir.
and let's say what you do is that let's say you put this object, you lift this object and place this object in here. So now you are applying some external force, right, to move this object. So whenever some other things are involved, so that are called the external part of the system, right? So that those are called the external agents. Understood?
Yes, sir.
So similarly, let's say you have a sun and you have this earth, right? So this sun and earth system are internal systems. These are part of the system, right? But let's
Yes, sir.
say, some other planet or other thing comes and then distort this system. So then this agent will be called the external agent, right? So
Yes, sir.
this is how you define the external and internal system. Is this part clear?
Yes, sir.
So then keeping these in mind, right? So objects which are part of the system are called internal. And the objects which are not part of the system are called external system, right? So this is what we call the external and internal. So this part is very crucial, right?
Yes,
So
sir.
okay, then the next topic
Sir, can
is,
you go up?
yeah. So you guys are noting it down. So then please note it down. So this is Earth and the object system, right? Earth and object system, and this is Sun and Earth system. Similarly, you have Earth and Moon system. So these are internal systems, right? When external things are applied on it, so those are called so the part which are not present in the system, those are called the external systems, right? So noted, guys, this part noted.
Yes, sir.
Yes, sir.
Okay, so now we can define this potential energy, right? So this is defined as the energy stored due to the position, orientation, and configuration by the object in space, right? So this is, let's say you have some object in here, right? This is placed over here and this has some certain configuration and this is kept at a certain height, right? So this will acquire some potential energy due to its position in this space, right? So we'll understand about that how do we represent this potential energy. So we'll see, right? Okay. And this is again, so this is only dependent on initial and final position, right? And thirdly, so this arises due to conservative interaction of the system, right? So why do we are calling it the conservative interaction? So let's say if you have a gravitational force, right? So this is a conservative force. So due to this gravitational force, there would be a potential energy called gravitational potential energy. Right. And let's say if you have this spring force, so due to this spring force, you have this spring potential energy. And due to electrostatic force, so electrostatic force, you have electrostatic potential energy. Right, so these are the examples of those potential energy, and they are only defined by this conservative forces. Is this part clear, everyone?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay, so let us understand about this gravitational potential energy. Right, so this is work done by, or let's say, so this is external work done by the uh, gravitational, or let's say by the external force to bring the object at certain height. Right, so let's say that you are bringing this object. Let's say you have this earth surface and you are bringing this object at this height, right? So this is the h height, and you are bringing this object in here. So the work done would be, or this change in internal energy, right? Change in potential energy, delta U. This would be work external, or this would be minus of work internal, right? So whenever I say external work done, so that would be against this internal work done. So what would be the internal work? So internal work done would be done by which force?
Negative work done by external force.
Yeah, that is true. That is true. That work external would be negative of work internal. But I am asking that this internal force, this internal work done is done by which force? What is the part of the system? What force is the part of the system? You have this Earth.
Gravitational.
Yeah, so this internal work done is due to gravitational, right? And external force, whenever you apply the force against this gravity, so that would be the external force, right? So let's say at this point there would be some u1, and at this point this is u2, right? So delta u would be u2 minus u1, and minus of what did we calculated in bringing this object to this site? What was the work done that we calculated? Do you guys remember? Yeah, what was the work done that we calculated?
Potential energy.
No, no. So potential energy is this one, u2 minus u1. This is the change in energy. Okay, let me in here. So this was the work done, right?
Yes, sir.
Minus mgh. Understood?
Okay, sir.
So this is minus of mgh. Okay. So then this would be mgh. And at this point, u1 is 0, right? So u2 is u. So your potential energy at that height would be mgh. So this is how you get the potential energy of the object at certain height. And that is dependent upon this internal work done or the external work done. Internal work done is due to this gravitational force, and external work done is whatever you apply against this gravitational. So is this part clear, everyone? This gravitational
Yes, sir.
potential. Okay, so where did we? Yeah, so please note down from. Yeah, whenever you guys want me to scroll down this, you guys please tell. So whenever you guys have noted, please tell me so that I can scroll.
Finish, sir.
Yes, sir, done.
Yeah, so in here you should write change in change in potential energy
Done, sir.
done. Yes, noted everyone.
Yes, sir.
Shida and Elam, what about you guys?
Yes, sir.
Okay, so then let us understand about another. So we understood about this gravitational force and the gravitational potential energy. So now let us understand about what is spring force. Right, so let's say you have this elastic spring, right? And you attach some mass with it. Okay, so let's say this is, so let's say this is the mean position, right? And you do two kinds of things. So firstly, you stretch this string, right? So then what you do is that, oh, this is a very bad diagram, but you guys just understand. So this was the mean position, and we have stretched this string this in this much. So this x distance we have stretched, right? And this has some mass. Okay. And then what you do is that you can do another thing, that you compress this string. So you can do this way also, right? So you are now compressing this thing. Okay. And let's say it is compressed by this x distance. So this is called elongation, and this is compression. So there is the property of this spring. There is this property of this spring to acquire its original position. So this is the best position that it has, this spring has. And whenever you elongate this spring, so it will want to acquire this position. So then in what direction it will apply the force to acquire this position, right or left?
So for like elongation,
Elongation, yes, elongation,
left.
left, right? So it will apply a restoring force in the backward against this motion of this object, right? Against the direction of this displacement, this will acquire the this will apply the force, and that force is called the restoring force, right? Similarly, for the compression, this will apply a force in this direction, right? Restoring force. And by Hooke's law, this force is given. So this force is proportional to the elongation distance, right? And minus of the elongation distance. Minus because it is always opposite to the direction of this elongation or compression, right? So then this force would be, when we remove this, so this is called the Hooke's law. And this force is minus kx, right? So this is called the story force or the spring force. And this is also a conservative force that we discussed. Okay. So now we have to find out what would be the potential energy of this spring, right? So what do we know? That work done internal, right, in bringing, so in bringing this object from here to here, right? That would be how much? So that would be fx fdx, right? Let's say from x1 to x2. Is this clear, everyone?
Yes, sir.
So now let us calculate what is work intern. F is minus kx, right? So this is x1, x2, and minus k is taken outside. So what is the integration of x? Do you guys remember? What is the integration of x?
Sir, x2 minus x1 by x.
Eh? Already, already you guys have forgotten.
0.
What is the integration of xn? Please revise
X
guys.
n plus 1
Yes, xn plus 1, and then
by n plus 1.
so from this property x would be x n is 1, right?
Yes, sir.
So this would be always remember this, right? So this should be in your fingertips because you always see this integral. So when we were doing the the differential method or the calculus method to prove the equations of motion. So we got v d, right? And then we wrote it as v square by 2. So please remember these things, guys, right? So this would be x square by 2, right? So minus x square by 2, and the upper limit and the lower limit. So if I write by 2 is here, so x square, x2, and x1. So what should be in here, guys? What should I write in here? First, I have to put
Sir,
the upper limit. So what should be in here?
sir, x2
X2 square
power. Yes, sir.
and minus x1 square, right?
Yes, sir.
So now you see that this internal work done, this would be how much? Minus of k by 2 and x2 square minus x1 square. And you see that in the first place, when I elongated the spring, so it was in here. So in here, at mean position, the x was 0. And let's say at this position, the distance is x. So x1 is 0 and x2 is x. right? So if I put these values, then this would be minus of k by 2 and x square. So this is my internal work done. Work done by the spring force. Understood?
Yes, sir.
So if I calculate the change in energy, this would be minus of W internal. So this is half kx square, right? And again, U2 minus U1. So at U1 position, my potential energy is 0. And at U2, this is, so the potential energy due to spring force would be half kx square. Is this part clear, everyone?
Yes, sir.
Okay, so please note it down and yeah, please note down from it. And if you guys have any doubts, please ask.
Okay, sir. Finished, sir.
Finished. Okay, then please note down this point. Yes, should I scroll down, guys?
Yes, sir.
Yes, noted everyone.
Yes, sir.
Yes, sir.
Okay, completed up to this much.
Yes, sir.
Okay, then let us understand about. So you already saw that from the work energy theorem, or let us repeat this one. So we saw that what is gravitational potential energy, right? And this is mgh. And we saw that what is spring potential energy. This is half kx square. So just remember this, right?
Yes, sir.
Okay. And we know that what is the work energy theorem. From work energy theorem, let's say, and this is the conservation of energy, and to be precise, mechanical. Okay, so work energy theorem, we have U, not U, but work done. This is equal to change in kinetic energy, right, guys?
Yes, sir.
Yes, sir.
And this is K final minus K initial, right? Okay. And similarly, just now from the potential energy, we saw that this potential energy is negative of work done, right?
Yes, sir.
So this is negative of delta K, right? So
Yes, sir.
U final minus U initial, this is minus of K final minus K initial, right? So we can write this as U final minus U initial, this is minus K final and plus K initial, correct? So we can write,
Yes, sir.
we can take it in this side and this is in this side. So K initial plus U initial, this would be U final plus K final, right? So what is kinetic energy plus potential energy? That is the total energy, right? So the total
Yes.
energy, this would be equal to final energy. So this says about the conservation of energy. So whenever we have the conservative forces involved, then the energy would be conserved, right?
Yes, sir.
So we will see two examples of this in our moment. So, but you guys please note down this part, conservation of energy part. Yes, whenever you guys have noted, then please. This is a change in potential energy, right? Yes, whenever you guys have noted it down, please tell.
Done, sir.
Done. Yes. Okay, Benela, what about you?
Yes, sir.
Okay, so now let us understand about this conservation of energy from first gravitational potential energy and then from the spring potential energy, right? So first, let us understand with this gravitational potential. So let's say you have this object, right? And you provide some initial speed to this object, and it reaches in here maximum height, right? And its speed becomes 0, right?
Yes, sir.
So let's say its initial speed is v, and the final speed becomes 0. So what is the third equation? What is the third equation of motion?
Sir, v square minus u square is equal to 2s.
2as. Good. So in this case, a is positive or negative?
Negative.
Negative. Good. So and let's say this height is h. So and v is 0. So this is minus u square, or let me write it as minus v square. And this is, I should denote it in this way, right? And this is
Sir, why v?
so I have projected or I have thrown it with speed v,
Okay, sir.
right? So minus of 2g and h. So this part cancels, right? So let's say if I take this 2 in this side, so this is gh, and I multiply this by m. So what I will get? I will get half mv square. This is equal to mgh. So what this equations tell? So whatever the energy, so energy at this point is how much? This is
Sorry,
what
sir.
energy at this point, total energy at this point is U1 plus K1, right? So this U1 is 0 and then this is half mv square, right? So E1 is half mv square.
Yes, sir.
And at this point E2 my energy has become how much? So at this point E2, that is U2 plus let's say K2. So E2 is U2 is mgh and plus 0, right? Because there is no motion at this point. So E2 is mgh. And from this equation, we saw that mv square is mgh. So this means that our E1 equal to E2. Is this clear?
Yes, sir.
So this tells the conservation of energy from the gravitational potential energy. So whatever the kinetic energy was at this point, this kinetic energy was stored in the form of potential energy at this point, right? Understood?
Yes, sir.
So this kinetic energy changed to the potential energy at this point, and let's say if starts to then drop down, then this potential energy will again be changed in this kinetic energy. right? So this is the conservation of energy from this gravitational potential. Understood?
Yes, sir.
Okay, so please note down this part. So this from the third equation of so we will do some questions in the next class, right? I have to speed up because the rest of the schools are doing this seventh chapter. So after this potential energy, we will have power and collision. So two topics would be remaining, and then we'll complete those two, and then we'll start this system of particles. So let's say this is one, this is two, and this is three. So from one, two, and three, we can say that E1 equals to. Whenever you guys have completed, now please
Finished, sir.
Ishita and Ram, what about you guys?
Done, sir.
So now let us talk about this spring, right, and spring potential. Okay, but before we do that, right, before we do that, so we understood that always. So in the case of this gravitational potential energy, so we understood that at every journey, right? Let's say this is some height h, right? And this is in the middle, right? Let's say in the middle. Let's say this is height. So this is the objective, right? So and this height is h by 2. And let's say you have thrown this object with velocity v, right? And in here the velocity is 0. So if I ask you that question is what is the velocity at let's say, what is the velocity at half distance, right? So how can we calculate this one? From the work energy theorem or from the conservation of energy, that would be very easy.
Yes, sir.
So how can we calculate that? We know that, let's say this is E1, let's say this is E2, and let's say this is E3. So we know that E1 equal to E2 equal to E3, right? So let's say that E1 equal to E3 using this one. So we have E1 would be how much, guys? Let's say this has mass m. So E1 would be how much?
Sir, like, how should we calculate it?
Energy at this point,
Maximum.
PE1 plus KE1. Energy at this point would be PE2 plus KE3. And energy at this point would be PE2 plus KE2, right? This would
Yes, sir.
be, so if I write energy at 1, so this is PE1 plus KE1. And how much is PE1 at this point? What is the potential energy? Yes, everyone, what is the potential energy at this point?
0.
Potential energy is 0. So this is the reference, right? From here we are, from here this object is at this height.
Sorry, potential energy mgh.
MGH, right? So why you guys are confused? Any confusion that you have? This we just did, right? At this point, potential energy is MGH. And okay. And what is the kinetic energy at this point? At this
0.
point, 0, right? So this is my energy at 1. Okay, let's say that this is 1. And I have, let's say E2. This is PE2 plus KE2. What is the potential energy at this point?
Sir, half mgh.
Half mg at this point,
Oh, last one. 0.
0, right? So this is 0. And kinetic energy is how much?
Half mv square.
Half mv square. So this is half mv square. So E2 is half mv square. Good. Now we have to find out what is the velocity at this point. So now let's assume that the velocity at this point is v prime, right? And we have to find out what is v prime. So let's write the total energy at third point. So that is PE3 plus KE3. Now what is the potential energy at this point? Yes, everyone now please tell. Rishita, Akib, and
Half mgh.
so, so Akib is saying MGH by half MGH. Rishita and Alam, what about you guys? Yes.
So same answer.
Same answer. So mgh by 2. Rishita, what about you?
So I'm still, I got that MGH by 2.
Mgh by 2. Good. So this is the height, right? Force is mg and height is h by 2. So mgh by 2. Good. Good everyone. And mgh by 2. And the kinetic energy at this point is will be due to this velocity v prime, right? And we know the definition of kinetic energy, so that would be half mv prime square. Understood, everyone?
Yes, sir.
Now this E3, E2, E1 all are equal, right? So from 1 and 3, what we can say that E1 equal to E3. So this is equal to mgh and mgh by 2 plus half mv prime square. So this would be how much? So this is mgh minus mgh by 2, and this is half of mv square prime. So this would be mgh by 2, and this is half of mv prime square, right? So then this 2 will cancel, and what we'll get? M will cancel, and we will get v prime would be equal to root of gh. So this would be the velocity in the half distance. This is part clear, everyone.
Yes, sir.
So from the conservation of energy, we can calculate these. And you could have also used this equations of motion. But from the conservation of energy, we can simply calculate this, right? So please note it down. And if you guys have any doubt, please ask.
So can you
So whenever you guys want me to scroll down the screen, you guys,
So can you scroll down? I'm done, sir.
Yeah, good. So, okay, so we will stop it here, right? And so the power and collision we will do in the next class, then this chapter will be